Welcome back to Nomenclature. Today we are naming ionic compounds with multivalent cations and hydrates. Take meaningful notes and come to class prepared. Many cations are multivalent. Most transition metals have several oxidation states. Manganese can have up to 7. The metals in group 14 also form multivalent cations. So here they are here and over here in group 14. When written, the oxidation state is given in Roman numerals following the cation in parentheses. This is called the stock system. So for example, copper can be copper 1 with Roman numeral 1 or copper 2 with Roman numeral 2. This means that copper 1 has an oxidation state of +1 or a charge of +1, and copper 2 has an oxidation state of +2 or a charge of +2. To write formulas for ionic compounds with multivalent cations, we use the same rules as we learned before. We write each ion, but we remember this time that the cation charge is in parentheses. Then we balance the charges as usual, and the rules for polyatomic ions still apply just the same. Let's do a couple of examples. Lead is Pb. It has a Roman numeral 2 next to it, so we know that it has a charge of +2. The oxide ion has a charge of -2. Let's balance the charges. We have a +2 on the lead side, and we have a -2 on the oxide side. So they balance each other, and my formula is PbO, because we need 1 lead for every 1 oxide ion. Tin 4 sulfide. Tin is Sn. Because of Roman numeral 4, we know it has a charge of +4. Sulfide is S with a charge of -2. So we have a total of +4 on the tin side, and we have -2 on the sulfide side. So I need 2 sulfide ions to balance the +4. So my formula will be 1 tin ion for every 2 sulfide ions. Let's practice some more. Iron 3 iodide. Iron has a Roman numeral of 3, which is why we have a charge of +3 over here. The iodide ion has a charge of -1. We balance the charges. We have a total of +3 for iron, and we have -1 for iodide. So I need 3 iodides to balance the +3 on the iron side. So my final formula is for each 1 iron, I need 3 iodides. Lead 2 nitrate. Again, lead is Pb. Roman numeral 2 tells me that the charge is +2. Nitrate is a polyatomic ion. Nitrate is NO3 with a charge of -1. We balance the charges. We have a total of +2 on the lead side and a total of -1 on the nitrate side. So we have to multiply nitrate by 2 to make it balance the lead. So my final formula will be 1 lead for every 2 nitrates. So I put it in a parentheses, close the parentheses, 2 nitrates. Now, to name ionic compounds with multivalent cations, we have to work backwards from the formula. We use a similar method as for regular ionic compounds, but the only difference is we have to determine the Roman numeral to indicate the charge on the cation. And then we need to express that charge as a Roman numeral in parentheses after the cation. So let's work an example to see. We have CoCl2. Co is cobalt. So I'll write cobalt. And then I need to put a Roman numeral in parentheses after cobalt to determine its charge. Then my anion is chloride, so I can write chloride. Now I have to figure out what is this Roman numeral in the parentheses. And what I do is I work from the formula backwards. In your formula, you will always know the charge on the anion. So you can separate your cation and anion. And if I look at my anion, it's chloride. I know that the charge on chloride is -1. Then I look at how many chlorides I have, and I have 2 chlorides. The total charge for my anion is -1 times 2 for 2 chlorides, and is -2. To balance the charges, I would have to have a +2 on the cobalt side. And since I only have 1 cobalt ion on this side, I know that my cobalt had a charge of +2. So my Roman numeral has to be 2, and I can put the Roman numeral 2 here. Let's practice some more. We have tin carbonate in number 1. How did we figure out that this was a 2? I can separate my cation and anion. I know that carbonate has a charge of -2. And I only have 1 carbonate anion here. So the total charge on the anion side is -2. Therefore, the total charge on the tin side has to be +2 for it to balance out. So my Roman numeral for tin had to be Roman numeral 2, and there it is. Number 2, we have SnF4. Again, Sn is tin, so I can write tin. Then I have to figure out the Roman numeral. And my anion is fluoride, so I can write fluoride. Now let's figure out the Roman numeral. Again, I split my cation and anion. I know from the charge on fluoride is -1, but I have 4 fluorides, so 4 times -1 is -4. Therefore, tin had to be +4 to balance out the -4. Therefore, we have a Roman numeral 4 for tin. So I can put Roman numeral 4 here. The next one is TiNO3 4. Again, I can separate my cation and anion. I have titanium. And then I have to figure out the Roman numeral. And my anion is nitrate. Now I know that nitrate has a charge of -1. And again, I have 4 nitrates. So I multiply that by 4 for the total charge. And I get -4 on the anion side. Therefore, tin had to be +4. Titanium 4 nitrate. Finally, we have FePO4. Fe is iron. PO4 is phosphate. And I have to figure out the Roman numeral. Then I separate my cation and anion. Phosphate has a charge of -3. I only have 1 phosphate ion. So the charge on the ion side has to be +3. And therefore, I have Roman numeral 3. Hydrates are ionic compounds that contain water molecules in the crystal. Most ionic compounds hydrate naturally due to water's attractiveness to charge, prevalence, and available binding locations in the crystal. The water is not part of the chemical substance, and this is reflected in the way the formula is written. When no water is bound to an ionic crystal, it is said to be anhydrous. So if we look at the 2 pictures below, we have copper chloride anhydrous on the left, which is a brownish color, and then we have copper chloride hydrated with 2 water molecules on the right, and it is a completely different color and blue. They look different, but they behave the same when dissolved in water. Something else you need to be aware of is an ionic compound is often referred to as a salt. So ionic compound is often called a salt also. Here is an example of a hydrate. We have cobalt oxalate attached to 2 water molecules. Now look at the crystal below. The water molecules are bound at specific intervals in the crystal. This changes the physical properties of the crystal, but no chemical difference is made. How do we write formulas for hydrates? We use the regular ionic naming rules. Then we follow the chemical formula by adding a dot and the hydrate preceded by the prefix number in the table below. You have to memorize the table. Mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa 6, hepta 7, octa 8, nona 9, and deca 10. So let's do an example. If we have sodium nitrite trihydrate, we first do the formula for sodium nitrite. Sodium is Na with a charge of +1. Nitrite is NO2 with a charge of -1. So the two charges balance, and that gives me NaNO3. Now I have trihydrate. Tri is 3 water molecules attached. So I put my dot, and then I put 3 H2O. Let's practice some more. Calcium carbonate dihydrate. Calcium is Ca with a charge of +2. Carbonate is CO3 with a charge of -2. The charges balance. So for each 1 calcium, I need 1 carbonate. Then we have dihydrate, and di is for 2 water molecules. So a dot and 2 H2O. Zinc sulfate monohydrate. Zinc is Zn with a charge of +2. Sulfate is SO4 with a charge of -2. The charges balance. So for each zinc, we have 1 sulfate. Now we look at our prefix. It's mono. Mono is for 1 water molecule. So dot H2O. Now how do we name a hydrate from a formula? Again, we use the same normal ionic naming rules, and we name the hydrate. Then we use the prefixes attached to hydrate. Let's see how that works. So if we have MgSO4.7H2O, Mg is magnesium. SO4 is sulfate. Then I look at my attached water molecules. I have 7 water molecules attached. So the prefix for 7 is hepta. So I say hepta hydrate. More to practice. GaF3.3H2O. Ga is gallium. And F is fluoride. So then I look at my attached water molecules. I have 3 water molecules. 3 is tri and hydrate. Lastly, I have Ni with C2H3O2 and 4H2O. Ni is for nickel. Nickel is multivalent, so I have to figure out the Roman numeral. Then C2H3O2 is acetate. Separate my anion and cation. I know that acetate has a charge of -1, but I have 2 acetates, so I'll multiply that by 2, and the total charge on the anion side is -2. So the total charge on the cation side to balance has to be +2. So I have nickel 2 acetate. Now I look at my water molecules. I have 4 water molecules. 4 is tetra. So tetra hydrate. This concludes our lesson for today. Please come to class prepared with good notes and your questions.